Alright, here is a problem which summarizes the entire unit. Which has a higher boiling point, CF4 or NF3? So we always start these by drawing the Lewis structures. And the first step in drawing the Lewis structure is to figure out your budget. So CF4 is our first. We look on our periodic table for how many electrons they have. Carbon is in the fourth column. It has 4 valence electrons. Fluorine has 7, except there are 4 of them, so we get to multiply that by 4. So we get our total budget ends up being 32 electrons there. NF3 will do, okay, so there's 5 from nitrogen, and then there's 7 in fluorine, but there are times 3, so 21 plus 5, your budget is 26. So your Lewis structure must match that budget. We identify the central atom. Again, the central atom is often the one that is unique or alone. Lacking that, it's often one that forms the most bonds. The one that forms the most bonds is typically the one that's farther from the noble gas. Carbon is 4 spaces away, so it likes to form 4 bonds. So carbon goes in the middle. And then we're just going to connect with single bonds to each of the atoms. And I'm going to do the same thing here with NF3, single bonds to each. And then I start by just making sure all of them follow the octet rule. So looking at this top fluorine, there are 2 electrons from this bond, so I need to add a total of 6 more to get it to 8. I do the same thing to this one, and this one, and this one. Carbon has 4 bonds attached to it, so it already has 8 electrons, 2 from each bond. Then I check my budget. My budget was 32. I count them all. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There's 32 electrons. This Lewis structure is correct. I'm going to have my dots here for these F's, so each F needs 6 to get to 8, because it already has 2 from the bond. Now nitrogen is in the middle. It has 3 bonds, so 2, 4, 6. It needs 2 more. Then I check my budget. My budget's 26. So again, there's 8 around here, 16, 24, 26. This is good. So my Lewis structures are correct. That's the first part. Now I need to find my shape. My shape is entirely dependent on how many groups are around the central atom. There are 4 groups around the central atom here, which creates a tetrahedral linear electron geometry. So carbon, there's a group going up, there's a group going here, down, and like this. It looks like a tripod with a top on it, and each of those has a fluorine. So this is a tetrahedral geometry, and that's the shape of this. Do the same thing with NF3. 1 group, 2 groups, 3. So it also has 4. So it also has 4 groups coming off it in a tetrahedral-like shape, which again is like a tripod with the top on it. The difference is this N only has a pair of electrons up here. It doesn't have an atom. So this we call trigonal pyramid. So it's basically a tripod. So these are the 2 shapes. Now I look at each bond in each molecule, and I decide whether it's polar or not. So in this bond, there's a CF bond, and they're all the same. I'm going to analyze C and F. So I look up the electronegativities of each atom. I do this on a chart or Google it, whatever, you can find it. Carbon's number is 2.55. Fluorine's is 3.98. I don't actually have to take the difference between these two, but it's about 1.4-ish. If it's 0.4 or over, the bond is polar, meaning that one atom is getting the electrons more than the other. Fluorine has a bigger number, so it is winning the electrons. So fluorine gets a partial negative charge, carbon gets a partial positive charge. The same thing is going to happen along every one of these bonds. Every one of these bonds is polar. Over here, same deal, I analyze N and F. N is 3.04. Fluorine is 3.98. I look those up. This difference is 0.4 or greater. This is polar. So fluorine's winning, gets a negative charge, N gets a positive. F gets a negative, F gets a negative. So they all have polar bonds, but are the molecules polar? The way you decide that is we're going to draw arrows from the positive atoms towards the negatives along each bond. Like this. And on this one, it's going to be like this. And then I look at these arrows and I ask, are they traveling in a general direction, or do they all seem to cancel? In this case, they're pointing in all different directions, down to the left, down to the right, up, all different directions, so they cancel, which makes this a non-polar molecule. Here, they might seem like they're going in different directions, but they all are generally pointed down towards the pyramid. So this has a general direction down, so this is a polar molecule. Another way to check this, it doesn't always work, but it works often, is if you can draw a line separating all the positive from the negative, so like all the positives on this side, all the negatives on this side, a lot of times that's going to be polar. So this line here, I can separate all my positive and negative, this is polar. There is no line I can draw on this molecule to separate the positive and the negative because the positive is embedded in the middle of this molecule, making it nonpolar. All right, last step. Polar molecules tend to stick together like magnets. They have what we call dipole-dipole forces, so they are more likely to stick together. Nonpolar molecules have what are called London dispersion forces. They're much weaker, so they're less likely to stick together. So the question, which has a higher boiling point? This one has dipole-dipole forces, and this one has London dispersion forces. Dipole-dipole are generally stronger, so it's probably going to hold them together better. So this one's probably going to have a higher boiling point, and that's it. So it's a somewhat long problem, but it encompasses a lot of material. And this right here, if you can do this, this pretty much summarizes the unit. So until next time, I am Derek Genova. Have a delightful day.